Welcome. My name is Felix Wäger. I'm going to share with you our approach of using the pump probe microscopy to get the elastic properties of a material. I want to start with a brief summary why we want to use this approach and what are the basics behind. Then I'm going to show you our microscope setup that we realized at our lab. Afterwards, I present the first results we acquired with the microscope in water and glass. And last but not least, a brief conclusion and a view on the following steps. We want to find a method to image materials, and there especially tissue, for example, ligaments and tumor tissue. The idea is to use the already observed interaction process of laser and material during ablation. Therefore, the laser is focused on the surface or inside of a body of a material, and by exciting the sample, shock waves should travel from that spot. By illuminating the sample sometime after the excitation, these waves should get visible. To make the waves visible for the human eye, some calculations are needed. First, we take a background image that is taken before excitation, here seen in image A on the left side, and an image a few nanoseconds after excitation, seen in image B in the middle at 10 nanoseconds after excitation. By calculating the difference image of these two images, we already can see the wave, but by applying an image filter, the result gets a little bit better, here seen in the images D and E. Now that we are able to visualize the waves in the images, let's talk about which waves may occur in the medium. In a solid body, there are two types of waves that can appear. First are the body waves, and there especially the P waves or longitudinal waves, which normally travel at a specific speed of sound. And second, there are the surface waves, and in bodies with definite endings, there may only appear the Rayleigh waves. Now that the two types of waves, body and surface, travel at different speeds and therefore occur at different times, they can be used to measure and calculate back on the elastic properties of the media, which is shown on the next slide. By measuring the two radii of the two waves, here seen on the left side, and the known past time after excitation, we can calculate the speed of these wave fronts. Those speeds, combined with the specific density of the material, can be used to calculate the elastic modulus seen in the formulas on the right. Now let me show you our microscope setup. We are using a single femtosecond laser at a wavelength of 1040 nanometers. And by focusing the laser in an SHG crystal, we generate a second beam path. The 1040 nanometer beam is used to excite the sample, here shown in red, and the beam at 520 nanometers is used to illuminate the sample. We also added an optical delay line to delay the illumination beam, and for imaging we are using a monochrome CMOS camera. The setup is special because we excite and illuminate the sample along one axis, and we are using microscope objectives with different magnifications to focus on the sample and take the color lighting to illuminate a big fraction of the sample. As first samples, we used water and glass because there are samples that take the steps towards hard and soft tissue. Now let me show you some of our results in water. We used water as an sample because of the well-known properties, and as mentioned before, it is a step towards soft tissue. The image you see on the left side was taken at a delay time of 15 nanoseconds. There, the wavefront is well visible and may be great to measure. To examine the properties of water, images were taken at 3 different delay times. Here shown 15.2, 11.5, and 4.2 nanoseconds after excitation, and at different pulse energies. The images on the far left show the wavefronts in water at the 3 different delay times and a low pulse energy. It is obvious that the fronts are merely visible. The images going to the right show the effect of the increasing pulse energies on the wavefronts, as they are getting more and more difficult to distinguish and therefore to measure. As a result, it is preferred to examine water at low pulse energies because the wavefronts are better measurable. The next sample imaged was glass, and first we focused the laser inside the volume. The image shows wavefronts at 2 different delay times and 2 different pulse energies. By looking at the images, it is already visible that the pulse energy has no influence on the wave's radius. This is also shown by the graph on the right side. Here we have the radius at the y-axis and the different pulse energies on the x-axis. The red graph shows the front at 11.5 nanoseconds, the black at 15.2 nanoseconds. By taking the difference of the radius and the delay times, it is possible to calculate the speed of these wavefronts, which comes in at almost 5,700 meters per second, which is comparable to the literature value. Now we are focusing the laser on the glass surface. The images show 2 different delay times, but now the same spot was excited more than 1 time. Doing so enables to widen the wavefront of the outer wave. Measuring the waves at different pulse energies and number of excitations at one spot is shown in the graph on the right. The outer wave's radius is neither affected by the pulse energy nor the number of excitations at one spot and is shown by the black graphs on top and bottom. The blue graphs in the middle show that the inner wave is dependent of the number of excitations and increases with the excitations. By calculating the speeds between the 2 delay times, it is shown that the outer wave is a longitudinal wave of the glass sample and the inner wave must be a wave in air. While examining the acoustic waves on the glass surface, another wave between the longitudinal wave and the wave in air got visible, here shown in the middle and nominated as second wave. The problem is, as seen in the image, right above the excitation spot, that the illumination had to be set that reflections of the used optics got visible in the image and the quality suffered. Also, mostly of the time, this wave is covered by the much bigger wave in air, which seems to travel at the almost same speed. After measuring the radius of this wave, it seems that it is actually a Rayleigh wave of the glass sample, and therefore could be used to calculate back on the elastic properties of the media as shown in the beginning. To conclude, we were able to image and measure acoustic waves in solid and fluid media. The results in water show that the wavefronts are highly dependent of the pulse energy. In glass, it was possible to image the longitudinal wave by focusing inside the volume and on the surface, and also when on the surface, a possible Rayleigh wave was visible. Now, what else is possible? We tried to image the waves in KZI, a ivory substitute, and with mammoth ivory to show the influence of the direction of growth of the dentine on the waves. Also, first tests with silicon were made where the crystal grid structure may have an influence on the wave front. Thank you very much for your attention, and I also want to thank my contributing team. With questions, feel free to contact me at the shown email or over the course of the online event. This slide is self-explanatory.